All right, lesson 9.2 is about inscribed angles, and this is one of the most crucial lessons for the entire unit. Inscribed angles are just going to come up in so many different ways throughout the rest of the time, so it's important that you understand this lesson. So we have to define an inscribed angle first. It's one whose vertex lies on the circle, and that phrase "on the circle," remember, means that it is touching the circle's edge, not inside, not outside, and whose rays both intersect the circle, in other words, two chords. So in this diagram, we are looking for two inscribed angles and the arcs intercepted, also known as subtended, by those angles. So to find an inscribed angle, what we want to do is take a chord, and I'm just going to get my highlighter going here. I'm going to take a chord, say chord DA, for example, and another chord that connects to the same point, so AB, and those have point A in common. So that would be considered an inscribed angle because the vertex of angle DAB is on the circle's edge. And to show the arc that it subtends, and that's a new term, subtend means an intercept. Intercept and subtend mean the same thing. It means an arc formed by the endpoints of that angle. So if I take this endpoint to endpoint, D to B, and make that little arc there, it kind of makes a snow cone. And this, I like to think of an inscribed angle as a snow cone angle. So you'll hear me say that once in a while. It's not a perfect snow cone because AB and AD are not the same. They're different lengths, so it's not a perfect cone, but you get the idea. This would be the top part, the shaved ice part, and the cone comes to a point. So to look for an inscribed angle, the one I just drew would be angle DAB. Okay. And so I could do another one, though. I could maybe say angle ACD, right? Starting at A, going to point C, going out to D. Angle ACD would be another one. So there are lots of them in this particular diagram. You might have come up with a couple different ones. So can two inscribed angles intercept or subtend the same arc? And the answer is sure. That one that I just named, if I highlight that one, that's going AC and DC. If I highlight that, the arc that it subtends is arc AD. Do that in a different color. All right, and then I can also take that same arc, those endpoints AD, and take them out to a different point. So I could say angle ABD. Right, angle ABD would have the same snow cone as angle ADC does. And so it's possible for an arc to be at the endpoints of two different inscribed angles. So yes, that is a possibility. The rays of these angles will be chords in the circle, and they'll intersect at a single point. Okay, so before we get into a certain relationship between that arc and the inscribed angle, you need to remind us of what the exterior angle theorem says. And that's saying if we have a triangle, and we make an extension line, the angle on the outside, the extension angle, is always going to be equal to the sum of the two remote interior ones, the two angles that don't touch that angle. All right, and so let's use that to prove why this fact holds true, that an inscribed angle will always be measured as 1/2 of the arc that it intercepts. Okay, so in this case, we're trying to show the angle BAC. Go down here and take that angle. BAC is angle 1, is half of arc BC up here. We're trying to prove that. So this is going to guide us through it. Why is triangle BMA isosceles? Well, if you look at triangle BMA, it's made up of two radii. BM and AM are both radii, so that's two equal sides, which makes an isosceles triangle, and therefore two equal angles as well. Angle 1 and angle 2 would be equal. So based on that fact, why should angle BAC be half of arc BC? All right, well, let's go step by step through this. First fact is that angle 3 is equal to arc BC. Think about that for a second. Why would that be? So if you think back to the last lesson, a central angle, one that's formed by two radii, is always going to be equal to the arc. Equal radii, equal arc. That's one way to remember that. Okay? So that's a statement from last time. We also know that angle 3 is equal to angle 1 plus 2 based on that exterior angle theorem. Right? If I extend that line beyond this triangle, the two remote angles sum up to the same as the exterior angle. Okay? Which means that exterior angle is also equal to 2 times angle 1. So what I'm basically doing there is saying because 1 and 2 are the same, that's equal to 2 angle 1s. We already know that BC and angle 3 are the same, so you can substitute that. And at that point, it's just dividing by 2 to prove what we were trying to prove, that angle 1 is half of arc BC. All right? So if we know that there's an inscribed angle, we can follow that angle out to make it snow cone, and the arc out here will be double the angle, or we can take the arc that we know, come back to the angle, and cut it in half. So cut the arc in half to get the angle measure. That relationship will always exist. All right, so exercise 3, we're trying to show that even if we are not building an angle off of a diameter, that concept still holds true. So arc BC and angle BAC have that 1/2 to 2 relationship. Okay, so based on exercise 2, what can we say about BAD and DAC? Well, angle BAD is an inscribed angle. It's 2 chords. One of them's a diameter, doesn't matter. It's 2 chords. So because of that, angle BAD has to be half of its arc. And same thing with angle DAC. That's also half of its arc. So we have that established. All right, so we're going to try to now prove that angle BAC, the whole thing, is equal to half of its whole arc. Okay, that's pretty straightforward because angle BAC is the sum of those 2 angles we just looked at. And so it must be equal to the sum of the 2 half arcs we said that those angles are equal to. And if I take out the half, factor out a half, I have a half times the sum. And so that since that sum of arc BD and arc DC is the whole arc BC, then the entire angle is equal to half of the entire arc. All right? So that basically tells us that the inscribed angle theorem holds true no matter how we build that inscribed angle. All right, so let's look at it a couple of different ways here. First off, in circle O, which means center point O, angle MOP is 18. We've got that. And we want to explain why angle MNP out here is 121. All right, so we're saying that this here is 121, trying to prove why that is. Well, if you look at this 118, it takes you out to this minor arc MP. That minor arc MP, I'm just going to color this in real quick here. That minor arc MP has to also be 118. And that's because central angles are equal to their arcs. So because of that fact, I can take the rest of the circle now, which is major arc MP. I missed the circle's edge there, but that's all right. That major arc MP is going to be equal to 360 minus 118. And so that's going to give us 242 degrees out here. Right? So now that I know that, let's see where else that 242 comes into play. Let me connect that endpoint M back to the circle's edge, and this endpoint P back to the circle's edge. And now you can see the inscribed angle that was formed there. These 2 chords, MN and NP, meet at point N. And so the arc that they subtend is this big major arc 242. So I can take half of that arc, is 121, because that's an inscribed angle subtending a major arc. So if an inscribed angle subtends a major arc, it's going to produce an obtuse angle. If it subtends a minor arc, it's going to produce an acute angle. All right, second to last example here. Circle K, center point K. Ratio of arc RT to arc TS is 2 to 7. It doesn't mean that they're 2 degrees and 7 degrees. It means there's some multiple of 2 and 7. So we fill that in. Determine the measure of angle TRS. All right, so TRS is here. And if you look at its endpoints, that subtends arc TS. So if I knew what arc TS was, I would be able to divide it by 2 to get angle TRS. So let's figure out what x is. If I add up the 2x plus the 7x, that's going to equal the entire semicircle. So that's going to equal 180 degrees. Now, how do I know that's a semicircle? Well, because it said circle K, tells me that K is the center, and any chord that runs through the center is a diameter. Diameter splits a circle in half. So that's how I know that that's a semicircle, or 180. 9x equals 180, x must equal 20. So if I take that over here, 7x would equal 140. Okay, so again, the angle I'm looking for is an inscribed angle, so it's going to be half of 140. It's going to be a 70-degree angle. All right, so measure of angle TRS is 70 degrees. Okay? And finally, explain why angle TWS must be the same as TRS. Let's find TWS. I'm going to take that down here to W and out here to S. It's got the same endpoints. It's still got T and S as endpoints, so we're intercepting or subtending the same exact arc. Any two inscribed angles that subtend the same arc would be half of the same arc and therefore equal to each other. So that's the reason. They are both inscribed angles intercepting the same arc. Therefore, they're half of the same value and equal to each other. We'll do a lot more with inscribed angles in class.